So, Tiago, if you please.
Sorry, I'm also learning text.
Sorry, excuse me, I didn't get that. What happened to the first presentation?
The first presentation was moved to session 9C.
Ah, I see. So
Sorry,
that's going to be
not
tomorrow.
It's on outside.
Sorry, I forgot.
Yeah, sorry, I thought it was QC or so.
No,
I think might have been something Portuguese that I don't understand.
At the very moment, it has to be moved to another session also. Sorry for not having warmed you up.
Thank you very much.
Welcome. Okay.
Okay, so I'll start.
Okay.
I'll be presenting this work called Advanced Fiber Optic Sensing Structural Monitoring System, which is a system that we developed under a European program called Moreira, and I'll be presenting all the developments regarding this system today. So this presentation is divided into 4 parts. The first one is the introduction, in which I'll talk about a bit of the motivation and the objectives, and the 2 technologies that you use for developing the system. Then in the methods I'll talk about the sensor parameter, the sensor placement parameter evaluation for the chosen sensors, the equipment and technologies used, and the test setup defined for the structural monitoring system. And then I'll talk about the 2 setups that we mounted and the results found for each of them. Finally, I'll present some conclusions and future works regarding this. So the main aim of this system is to do maintenance and preventive maintenance, so to avoid blade failure and reduce the downtime due to maintenance. Also, this will extend the wind turbine blade working life. So the objective for this work in the context of this project was to design a laboratory scale monitoring system for representative component blade. So the technologies used were all fiber technologies, and we used 2 types of technologies. The first one are FPG technology, which is fiber grating, which is an optical fiber sensor that can evaluate pressure, temperature, or strength, depending on the interrogator used and the specifications of each interrogator. So this works so we have the fiber with several markings, which work as mirrors of multiple layers of alternating materials with very refractive indices. And then you push a laser to the fiber and assess the reflected frequency of the laser, and through the shift of the frequency you can assess all of these parameters. The greatest advantage of these technologies compared to, for example, regular strain gauges are its small size, faster response. It allows for a more distributed senses, and it has immunity to electromagnetic fields. It also works underwater, which is a great advantage. The other used technology is also a fiber optic sensing technology, which is, in this case, this is the more broad nomenclature, DFO, so distributed fiber optic sensor, which can assess temperature or strain both along a continuous fiber. This uses the principle of functioning of the system is relapse current wave technology, which uses scattered lights from the particles of the fiber that it measures as the other one, the reflected light. And so in this sense it does like an initial marking of all the scattered light to the push of the laser, and then the deformation of the laser will change this marking and will allow for the measurement of both strain and temperature all along the fiber. This has the great advantage of not having to add marks, so you can use all the fiber and much bigger fibers up to, let's say, 50 meters. So again, the advantage is the continuous distributed sensing and no need for markers within the fiber. So we apply these 2 technologies for developing a sensing system for a wind turbine blade. Use the standard EEC 61400 which is the one used for measurement of mechanical loads of wind turbine blades, and we choose to assess the blade root moments and the moment distribution along the blades. For the blade root analysis, we place 4 FPG sensors in the root, and for the moment distribution, we placed a continuous DFO line along the edges. The chosen equipment we use for doing these assessments are the solution of the DFO of Luna, so the Luna of the interrogator plus the sensor that comes included with it. And for the FPGs, we use FISense interrogator with also the corresponding sensors. So for doing the assessment, we did 2 assessments, one which was the geometry assessment setup, in which we produce a blade by additive manufacturing PLA, just to place all the sensors in the corresponding position as it would in a real blade, and for ensuring the placement techniques and glues used, we had some material sand bias on the blade that is to be produced, and we tested also the application of sensors in these blades to ensure no issues would occur. Regarding this material compatibility test, so we had a sample in which we placed a fiber optic fiber with 4 sensors that we then tested in deformations up to 200 microstrain and find no decoupling of the fibers, and all the results were within expected, so it enabled us to conclude that the sensing system would not fail in the appliances on the real material of the blade. Then we did the geometry setup in which we placed the 4 sensors in the root of the blade as planned, and the DFO line across both the leading and the trailing edges of the blade, and we again did testing in both the configurations of the blade, so this and rotating 90 degrees in loadings up to 9 millimeters, and we found that no issues occurred in our sensing system and that the results were within expected. So this is our examples of the results from the FED blade. In here we have the continuous placement done here, and in here we had some sporadic loadings just to see what happens. And in this case we have the deformation along all the line of the DFO in 3 different times of these tests done. So in general you can say that a version of this monitoring system that is to be implemented in a real life blade was done using both FPG and DFO sensing technologies. All the variables considered essential were monitored successfully, and we carried the setup that would assure that our system would work correctly. At the moment we are working on doing a software for doing a more profound analysis on the results that would allow, for example, counting cycles for fatigue analysis, or do event detection such as impact detection and other kind of this kind of situations. And this will be all from my side. If you have any questions.
Thank you, Tiago, for your very interesting presentation. Questions to Tiago in English? Yes, please.
Can you tell me what are the costs of these sensors?
Which one?
Both, let's say.
So the FISense, this solution is actually very cheap, so I would recommend this company. I think it's a German company, and for the interrogator we can say like 1,000, and for the sensors it really depends on the length of the amount of sensor that you use, but we can say 200 for like 1 meter fiber with 4 sensors, and as used here. For the DFO solution it's very expensive in comparison, so the interrogator with only 1 channel costs something like 70 grand. And then for the sensors, let's say for a 1 meter fiber or 2 meter fiber like the one we use here, something between 300 and 400 euros. Okay. So this would be more or less the cost. In terms of DFO, this is kind of the only player in the market, but for FPGs, there are way more expensive solutions also.
Thank you. Another question is, what is the dynamic range of these sensors in terms of frequency?
For frequency analysis, I'm not really sure, but for sure it's a very high number, especially comparing to, for example, strain gauges or stuff like this. But in this case, as it's for a very big components, such as a wind turbine blade, we did not have that concern in mind. But for sure, it's a very high number compared to regular sensors, at least for strain measurements.
Thank you.
What's the resolution of the fiber?
In terms of what strain measurements or the continuous one because the resolution for which perimeter more specifically?
On the lines.
Okay, so
for measurement for it.
yeah, the FPG is a discrete sensor, so you put the FPG marking in that place, and it's kind of in that place is in the micro range of error. But for the DFO, they say it's continuous, but it actually has an error because I suppose they measure in time, so they do pulses of lasers and then measure the backscatter in time, and it has some error associated. They say the error could be up to 1 millimeter, but in fibers that can be up to 50 meters. So this is the manufacturer's statement.
Thank you.
Okay, we have one probabilistic activity. The system is immune to external electromagnetic disturbances.
No, one of the advantages of using optical fiber is not sensible to that kind of effects, as for example strain gauges are. So in this case, we believe that you will not be affected by that kind of phenomenon.
So for example, for a location in an offshore position, in case of a lightning is fine, it will not affect the...
If the interrogator equipments are isolated, yes, but if the interrogator equipment are affected by that kind of phenomenon, I'm not sure they will survive.
Thank you so much.
Okay, thank you.
We are moving to the next presentation, if you do not mind. Next work is entitled Fracturing and Degradation Study of an Earthen Historical Wall.